satellites, radio and TV broadcasting. Then they are used in the most important, which is the weather forecasting, remote sensing, and GIS. So these are the different applications of satellites which are being used nowadays and in the past. So the weather forecasting is a major development of the satellite which was being launched recently by the ASRO system. So now let us see the contents of this presentation. So the contents of the presentation starts with the Kepler's law, Newton's law, the orbital parameters, the orbital perturbations, station keeping, geostationary orbits and the non-geostationary orbits. Then we'll be seeing the look angle determination, the limits of visibility of eclipse, the subsatellite point sun transit outage, the launching procedures, launch vehicles, and propulsion system. So these are the contents for Unit 1 and in the same presentation. So first of all, let us see what is an orbit. So you can see you can see uh, there is a plus at the center. So that is the center, and around the plus there is a circle of white. You can see. So then around that there is a ring, a red color ring and a white dot. So this is what we call as an orbit. So orbit is a difference in mass orbiting a common barycenter internal to one body. So difference in common mass orbiting a common barycenter internal to one body, which is similar to the Sun Earth system. So the Sun is at the center, Earth is revolving it. So it is an orbit. உங்க பேர் இல்லையா செக் பண்ணுங்க
அந்த யூனிவர்ஸ் ஒர்க்கு எனக்கு இந்த வேலையை ஆஃபீஸ் வேலையும் சரியாக இருக்கு.
செக் பண்ணிடுறேன் சார்.
ரெண்டு செஷன்
காலைல 2 வாட்டி ஃபோன் பண்ணீங்க. ஃபோன் பண்ணிட்டு வேற யார்கிட்ட பேசிக்கிறீங்க?
உங்ககிட்ட சொன்னேன் சார், பட்டுன்னு வச்சிட்டீங்க. அதுக்குள்ள
என்ன ஒண்ணுமே சொல்லல. ஹலோ ஹலோன்ற யார்கிட்டயே பேசிக்கிறீங்க.
பட்டு வச்சு
என்ன சொன்னீங்க?
இருங்க சார் சொல்றது பட்டுன்னு வச்சுங்க.
இங்க வரணும் சார் உங்களுக்கு. இங்க வரணும். இங்க தானே வரணும்.
இதுல வரணும்.
இங்க தானே வரணும்.
ஒரு பரிவு நம்பர் இருக்கு.
நம்ம டிபார்ட்மெண்ட்ல ஒரே ஒரு பரிவு நம்பர்.
இது ரெண்டு செஷன் இருக்காங்க.
இங்க தான் சார் வரணும்.
இது ஒரு செக்ஷன்
நான் போட்டுறேன். இது மட்டும் மிஸ் ஆயிடுச்சு. நான் சார்கிட்ட சொல்லிட்டேன் சார், மிஸ் ஆயிடுச்சு சார் அப்படின்னு சார். நீங்க இங்க போட்டாலே நீங்க ஆப்ஷன் தான் இருக்கும். நீங்க கேட்டீங்க ஆஃபீஸ் ஆஃபீஸ்.
சரி சரி, அங்கே தான் இங்கே 7,000 பாருங்க, அங்கேயே சரியா
இல்ல நான் கேட்டது சொல்லிட்டாரு.
ஆப்ஷன் போட்டு அங்கேயே
நான் உங்களுக்கு இதில் ஆட் பண்ணி கொடுத்துறேன் சார்.
கொடுத்துட்டு அப்பதான் லோடு காமிக்குது, எனக்கு பிரச்சனை இல்லை.
அதில் போட்டுட்டேன். இல்லை நான் அதில் போட்டேன், இதில் வந்து மிஸ் ஆகிட்டு இருக்கு.
7,000 நான் திட்டாங்க.
இங்கே தான் சார் வரும் உங்களுக்கு. Thursday 4 நம்ம ஃப்ரீ தானே?
நாளைக்கு எப்பயுமே நான் ஃப்ரீ கிடையாது. அங்கே உட்காந்து போய்
இல்லை அப்போ ஒர்க் லோடில் ஃப்ரீ தானே? நான் போட்டுடுறேன், சார்கிட்டே சொல்லிட்டேன், அப்டேட் பண்ணிடுறேன். ஒரு 2 நாள் டைம் கொடுங்க, அப்டேட் பண்ணிடுறேன்.
கேமரா மட்டும் ரெடி பண்ணி அது மட்டும்
சரி. ஒரு 1000 ரூபாய் வாங்கி கொடுத்துருங்க உங்களுக்கு.
எப்படி சார் கிட்டுக்கு சார் நீங்கள் வச்சுக்கிறேன்னு சொன்னா கேட்குறேன்.
மைக் ஆஃப் பண்ணுங்க.
அப்புறம் பேசுகிறேன்.
So another example for orbit, you can see barycenter at the center, can see a plus at the center. There are two orbits. You can see two orbits, two bodies with the same mass. The same mass. You can see that white and this white, they are the same mass. So two bodies with the same mass orbiting a common barycenter, and these two are external to both the bodies. So the first one which I had shown is your internally. Internally they are orbiting. Now this shows externally they are orbiting. So with the eccentricity, elliptic orbits, which is a common situation for binary stars. So another example I'll show you. So this one. So with the barycenter, yeah, the plus is your barycenter. Plus is your barycenter. So there are two orbits. One, the first diagram you can see, one mass body is revolving, another mass body is revolving with the barycenter. You can see that two in two different. Then next image you can see that there are two revolving around the barycenter in the same orbit, two bodies. Then you can see the barycenter is moved, okay, and the mass of the orbit, mass of the body in the orbit is smaller, and you can see that the mass of the body with respect to barycenter is very much larger. So these are called, these are your orbits. Orbiting is revolving. I think Mukesh saw. The meaning of orbiting is that any body moving in elliptical or in a particular shape, in a particular shape with another. So that's what I had showed that in red plug. So one body is revolving around another body. And most of the cases, the satellites revolve in elliptical path, following eccentricity. Okay, I think, okay, sure. Okay, right, thank you. So any other queries? If there are no further queries, I will proceed on to the next slide. The Kepler's law. Okay, thank you, Sai Ganesh. The Kepler's law, the first Kepler's law, which is used for planetary motion, is that the orbit of any smaller body about a larger body is always an ellipse. So this is what the orbiting takes place in elliptical format. It follows eccentricity. So the orbit of any smaller body about a larger body is always an ellipse. So with the center of mass of the larger body as one of the two focus. So this is the first Kepler's law. The second Kepler's law states that the orbit of a smaller body sweeps out equal areas in equal time. Second Kepler's law states that the orbit of the smaller body which sweeps out equal areas in equal time, which is Kepler's second law. So we'll see that. So this is how it works on. So there are two focus points. The focus one point is considered as sun. Focus 2 point is the point or the earth from where we view it. Okay, so the planet moves from one point to another point. Consider from P1 to P2. So that we take it as area 1. Consider it as area 1. So the same planet which is orbiting the sun, it is measured at a same time. So right from P3 to P4 in an elliptical path will show that the area being covered will be equal to the area covered from P1 to P2. So you can see from the diagram is that the green area is equal to the blue area. So area 1 and area 2 will be equal. So the planet is moving here very much closer and here very much farther, farther away, but within the same specified time. Okay, so this is your Kepler's law. So you can see that an image of a satellite revolving around the Earth. And this satellite focuses on the Earth for a particular geographical area. So next is the Kepler's third law. We have three laws. The third law is that the square of period of revolution of a smaller body about the larger body equals a constant multiplied by the third power of the semi-major axis of the orbital ellipse, which is given by the formula t square. The square of the period of the revolution, which is equal to 4 pi square a cube divided by mu. So a is your semi-major axis of the orbital ellipse. So we'll see that how do we get this. So these are the three laws. This equation determines the period of any satellite. So this period is used in every GPS receivers in calculation of the positions of a GPS satellite. So this Kepler's law was developed by John S. Kepler. He developed the three laws that describe the motion of the planets across the sky. One is first law, which is we have seen law of orbits. Second one, law of areas. Third one, the law of periods. So this is what we have seen. First Kepler's law, second Kepler's law, third Kepler's law. So the short description of this Kepler's law is that the first one, all planets move in elliptical orbit with the sun at one focus. This first law. Second law is that law of areas, or Kepler's second law. A line that connects a planet to the sun sweeps out equal areas in equal times. For example, if you're taking for 10 minutes from P1 to P2, that area whichever is being covered, and with the same 10 minutes after some duration, if you take P3 to P4, both will be equal. So that is your second law. Third one is your law of periods. The square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. So which is law of periods. So you can see the law of orbits here. So I'll be back in a few minutes. Kindly be awaited. So this diagram shows the law of orbits, which is the first one. You can see. So here we have the sun, which is being present, which is shown in orange color. Then we have the distance between the center of the ellipse to the outer point, which is the semi-major axis of the ellipse called as A. Then the distance from the center of the ellipse to the point of sun, where the center point of the sun is measured as EA, E into A. This A, E is the opposite focus of the ellipse. E is the distance being measured from the center of ellipse to the opposite focus of ellipse. So that distance is E, which is the eccentricity of the ellipse. So that place the sun will revolve. Okay. The farthest point from the sun when an earth is rotating. So you can see in the ring, you can see in the ring, a mass body is being rotating. Consider this as earth. So the farthest point from the sun to the earth is measured as aphelion, or we call it as apogee. And the shortest point from the distance of the sun is called as perigee. So the distance between the perigee point to the center of the sun is RP. Okay, and the distance between the farthest point of the Earth orbiting to the center of the sun is RA, which is RA. RA is your farthest point distance. So this RA can be calculated by A of 1 plus E, whereas the smallest point or the shortest distance of the rotation of the Earth is measured as RP, perigee, which is A of 1 minus E. So this is law of orbit. So next is the law of area. A line that connects a planet to the sun sweeps out equal areas in equal time. So, so for an entire duration of P1 and P2, mentioned in violet, here you can see the sun at the center, the earth is orbiting at different time axis, it is being measured. So if I measure for a particular time interval at this point, the same at perigee, during the perigee would be equal to the same time duration during apogee. So this is law of areas in diagrammatic representation. So next is the angular moment of a particle. So this angular moment of a particle with respect to the mass m is being chosen from the origin. Okay. So it is given as L is equal to mvr sin theta. So we can write this in the form of vector product as L is equal to r cross p. R cross p. So where the direction is given by the right hand rule, which would give L the direction out of the diagram, and for orbiting an angular momentum is conserved. So this leads to one of your Kepler's law. So L will become mvr. So what is this angular momentum? The angular momentum is the same at every point on an orbit. Same at every point on an orbit. When it is closer, it increases its speed. So when it is farther, it moves away. So you can see in the diagram the angular moment of a particle. The angular momentum is the same at every point on the orbit. So it is closer, it increases its speed. That's all. The remaining all will remain the same. Next is the law of period. You can see in x-axis the square of orbital period measured in year square, and in y-axis it is a cube of semi-major axis AU cube. So the period right from Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, but all the planets are being placed. So the semi-major axis, a straight line represents the Kepler's law of periods. So this period is being given by T, which is the Earth years. So with respect to the Earth rotation and the period of rotation, it is being evolved. So T square is equal to 4 pi square divided by GM A power cube. A power cube. A power cube is the astronomical units being measured for the entire Earth, which is the semi-major axis. So T is measured with respect to the Earth years. So M is your solar masses, depending upon the planet. So this can be simply expressed as a T square is equal to A power the whole cube. So when considering 4 pi square divided by G is equal to 1. So next topic is your geostationary orbits. So geostationary orbits which are perfectly having eccentricity is equal to 0, it is considered to be a circular. So it must be at correct altitude having this correct period. So it must be in the planar way of equator having zero inclination with respect to equator. So then we call it as an orbit which is being placed as perfectly geostationary. Then next is the geosynchronous orbit. If the inclination or the eccentricity, which is E, which we are seeing, is not equal to 0, then orbital period is correct, then the satellite will be in geosynchronous orbit. If inclination or eccentricity is not 0, then the satellite is in geosynchronous orbit. So the next terminology is about apogee and perigee. So which we are saying. So the farthest point from the measurement of the satellite to the Earth, farthest point you can see. Earth is present here, it is revolving in its own axis, and satellites revolve in an orbit. So the distance from this satellite, which is at the right hand side, okay? So from this distance to the Earth's surface, this distance is apogee, and this point of the satellite is called apogee point. And this satellite on the left hand side is closer to the Earth's surface. You can see that. So this point is called as perigee point. Okay, apogee and perigee. So apogee is the point in the orbit where the satellite is farthest from the Earth is called apogee. Perigee is the point in the orbit where the satellite is closest to the Earth is called perigee. Always the apogee and perigee are always opposite to each other. The orbital period of a geosatellite is around 23 hours, 56 minutes and 4.1 seconds, which is considered to be as one sidereal day. So a solar day is approximately 3.94 minutes longer than a sidereal day, which is 24 hours. So we calculate it with respect to 24 hours. So 3.94 minutes is longer. So this is the orbital shape and size parameters. So apogee and perigee You can see. Now I have drawn the Earth from left side to right side. I have drawn it. Now you can see the Earth surface. Here it is closer to this rotation of the satellite. So this is called as perigee, and here it is farther. It is called as apogee. It is apogee radius and apogee altitude. You can see. So some of the parameters. The semi-major axis. These are the parameters. Semi-major axis, apogee or perigee radius, apogee or perigee altitude, period, mean motion. So semi-major axis defines semi-major axis defines the half the distance between the 2 points in the orbit that are farthest apart. Apogee and perigee radius is measured from the center of the Earth with the points of maximum and minimum radius in the orbit. The apogee or the perigee altitude are measured from the surface of the Earth with the points of maximum and minimum radius in the orbit. So it is a theoretical sphere with radius equal to the equatorial radius of the Earth. So period is the duration of one orbit based on assumed two-body motion. Mean motion is the angular speed required for a body to complete one orbit counted as per solar day, which is 86,400 seconds. So 86,400 is your mean motion based on a two body motion, so which is approximately equal to 24 hours. So when you take 24 hours per day, it is 86,400 seconds. You can calculate. So next is the eccentricity. Eccentricity, the shape of the ellipse comprising the orbit ranging between a perfect circle and a parabola. So from a perfect circle to a parabola, will have a value. So that value is your eccentricity. So eccentricity is equal to 0 is a circular, and if it is equal to 1, it is a parabola. So next is the look angle determination. The surface of the Earth is divided up into grid-like structures. Okay, you can see grid-like structures, which is latitudes and longitudes. Latitudes are the angular distance measured in degrees north to south, so top to bottom on the map or on the globe that we see. Longitude is the angular distance measured in degrees from a given reference longitudinal line. So it is east-west. So the latitude of 90 degree is represented as n is equal to 90 degree. Example. So you can see that. So this is an um, look angle determination of equator at the center. You can see that 0 degree. Okay, which is your longitude, which moves from east to west or west to east. You can see the degree center. Equator. Then we divide it into Tropic of Capricorn, Tropic of Cancer, and many more. So at the center you have this point in red color, which is moving from north to south. This prime meridian. Okay, prime meridian. So 0 degree. So this side, left side 30, 60, 90, 120, 150, 180 it goes on, and at the right side it goes on similarly, just as you would have seen in your history globe. So latitude and longitude. So these are very much important in look angle determination of a satellite. Such that the GPS satellites works on. locating the exact points. These are imaginary lines. So the coordinates to which an earth station antenna must be pointed to communicate with the satellite. The coordinates to which an earth station antenna must be pointed to communicate with the satellite is called as look angles. So the look angles are commonly expressed as azimuth, AZ, and elevation E1. So the azimuth is the measured eastward from geographic north to the projection of the satellite path on a horizontal plane at an earth station. So the elevation is the angle being measured upward from the local horizontal plane at the earth station to the satellite path. You can see that. So the satellite is being placed in space. So this point, the center is here, is the local vertical, so which is projecting towards the north. Okay, I keep an antenna here at this point projecting towards the north. So path to the satellite is measured from the antenna to the satellite. So it is path to the satellite. And the projected angle, projection of path onto the local horizontal plane is EL. So the definition of elevation EL and azimuth AZ, the elevation angle is measured upward from the local horizontal at the earth station, and the azimuth angle is measured from true north in an eastward direction to the projection of the satellite path onto the local horizontal plane. The next is the subsatellite point. The subsatellite point is a location on the surface of the Earth that lies directly between the satellite and the center of the Earth. This is the point called nadir point. Nadir point directing from the satellite. So for satellite in equatorial orbit, it will be always located on the equator. I'll show you the nadir point. So this is the nadir point. So satellite focus to the Earth. So zenith and nadir pointing directions is being shown here. So zenith direction is the direction where the line joining the satellite and the center of the Earth passes through the surface of the Earth at each point. The satellite is directly overhead at this point, and so an observer at the subsatellite would point would see the satellite at zenith at an elevation angle of 90 degree. So the pointing direction from the satellite to the subsatellite point is the nadir direction. If the beam from the satellite antenna is projected at a location on the Earth which is not at subsatellite point, the pointing direction is defined by the angle away from nadir. So in general, two nadir angles are given. One is the number of degrees north or south from nadir, and the number of degrees east or west from nadir. So east, west, north, and south are directions. Those are defined by the geography of the Earth. So with respect to that, the zenith and the nadir directions are being defined. So zenith direction is the direction from where the satellite and the center of the Earth passes through the surface. And nadir direction is the direction from the satellite, with respect to the satellite, from seen there to the point where the observer sits. So this is your nadir point. Always the zenith path and the nadir paths are opposite in directions along the same path. So viewing from satellite is your nadir, viewing from the Earth surface to the center is your zenith path. So to an observer of a satellite standing at a subsatellite point, the satellite will appear to be directly overhead. And the designers of the satellite antennas refer that the pointing direction of the satellite antennas beams to standard direction, which is very much important concept. So next is the orbital elements. If you're having any other queries till this presentation, you can type in chat box. So M in the law of period is the solar mass. M. Okay, solar mass. It stands for solar mass.
Okay, sir. But what about M, sir? When T square equal to A cube? Here you said 4 pi square by G equal to 1. What about M, sir, there?
Can you kindly type in chat box? I couldn't get you properly. Mukesh, kindly type in chat box. No, I couldn't get your query, so kindly type in chat box.
Hello, sir.
So, any other queries? Uh, Thank you, Mukesh, for your valuable query session. Any other queries from anybody? If no queries, the attendance link for today's session is given in chat box. Kindly fill it. Only those who fill this link will be given attendance.